Welcome to the fundamentals of thermodynamics, where we explore the intricate world of heat, temperature, and pressure. This presentation will guide you through the essential concepts and applications of thermodynamics in various systems, crafted by LARK Labs. Heat energy constantly moves between substances and molecules, creating the thermal interactions we experience daily. To measure these interactions, we use temperature measurements rather than simple terms like hot or cold. In refrigeration and HVAC systems, precise temperature gauges are essential for monitoring system conditions accurately. Temperature is a measure of heat intensity or thermal energy level in a substance. We use different systems to measure temperature, including Fahrenheit, Celsius, and Kelvin. Absolute zero represents the point where all molecular movement stops, marking the lowest possible temperature. The Fahrenheit scale is prevalent in the United States for everyday temperature measurements, while Rankine is used in thermodynamic calculations. Celsius and Kelvin are widely used in scientific applications, with Kelvin being the absolute scale for scientific precision. Converting Celsius to Fahrenheit involves a simple formula. Multiply the Celsius temperature by 1.8 and add 32. This conversion is crucial for understanding temperature differences in various scientific and practical applications. To convert Fahrenheit to Celsius, subtract 32 from the Fahrenheit temperature, divide by 1.8, and you have your result. This conversion helps in aligning temperature measurements across different systems and regions. Heat follows fundamental principles. It cannot be created or destroyed, only transferred or converted. It can be precisely measured and accounted for in thermodynamic calculations, transferred between substances, and naturally flows from warmer to cooler areas. The British Thermal Unit, BTU, is a standard measure of heat energy in the English system, widely used in HVAC and other thermal applications. It represents the energy required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. Conduction is the transfer of heat through direct molecular contact, occurring between molecules within a single substance or between substances in contact. Different materials conduct heat at varying rates, influencing how we perceive temperature. Copper, an excellent thermal conductor, efficiently transfers heat along its length when placed in a flame. This property is crucial in heating and cooling applications, such as heat exchangers and thermal bridges. Convection involves the transfer of heat through fluid movement, driven by temperature differences. It can occur naturally or be forced, playing a vital role in heating systems and atmospheric phenomena. Baseboard heaters use natural convection currents to distribute heat efficiently throughout a room. The heating element warms the air, creating a circulation pattern that gradually warms the entire space. Radiant heat travels through air without heating it, transferring energy to the first solid object it encounters. Unlike conduction and convection, radiation can travel through a vacuum, making it unique in heat transfer. Space heaters utilize radiation to transfer heat, emitting infrared radiation that warms objects in its path. This method is efficient for heating specific areas without affecting the surrounding air temperature. Sensible heat results in a measurable change in temperature directly measured with thermometers. It represents the energy required to change the temperature of a substance without altering its state. Latent heat causes a change in the physical state of a substance without changing its temperature. This hidden heat is crucial in processes like melting and vaporization, where temperature remains constant during state changes. Latent heat includes vaporization, condensation, and fusion, each requiring energy to change a substance's state without altering its temperature. These processes are vital in refrigeration and air conditioning systems. Water's response to heat involves sensible heat regions, where temperature changes, and latent heat regions, where phase changes occur without temperature variation. This relationship is crucial in understanding heat transfer in water. Specific heat is the energy required to raise the temperature of a substance by 1 degree. Materials like water have high specific heat, making them excellent for storing and transferring thermal energy in heating and cooling systems. Sizing heating equipment involves calculating the heat required, considering the weight of the substance and the specific heat. This formula is essential for designing efficient HVAC systems and industrial processes. Let's dive into the calculation example for sizing heating equipment. Imagine needing to heat 1,000 pounds of steel from 0 degree dwarf to 70 degree. How much heat is required? Using the formula Q equal Wx specific heat x dt, we find that 8,120 BTU is needed. This example highlights the importance of understanding specific heat and temperature change in heating applications. Pressure is a fundamental concept in physics, defined as force per unit area. For instance, if a 100-pound weight rests on a 1 square foot area, the pressure is 100 psi. This principle is crucial in understanding how different surfaces can withstand varying forces. This illustration shows how the same weight can exert different pressures based on the contact area. A 1-pound weight on a 1 square inch surface exerts 1 psi, while a 100-pound weight on the same surface exerts 100 psi. This concept is vital in engineering and design. Atmospheric pressure is the weight of air above us, and Torricelli's experiment with a barometer demonstrates this beautifully. By measuring the height of mercury in a tube, we can gauge atmospheric pressure, which is typically around 760 millimeters of mercury. The mercury barometer is a classic tool for measuring atmospheric pressure. At standard atmospheric pressure, mercury rises to about 29.92 inches. This measurement is crucial for weather forecasting and understanding atmospheric conditions. Pressure gauges are essential in HVAC applications, helping to monitor and ensure system efficiency. Board-and-tube gauges and digital measurement gauges are commonly used to provide accurate pressure readings. The board-and-tube mechanism is a fascinating device used in pressure gauges. As pressure increases, the tube straightens, moving a needle across a calibrated scale. This simple yet effective design is widely used in various applications. The board-and-tube has been a reliable tool for over 170 years, thanks to its simplicity and accuracy. This photograph showcases its characteristic curved shape, which allows for precise pressure measurements in diverse settings.